Okay, so we come to our next speaker, and the topic also fits to what we've seen before. So the next speaker is Evelien Symoens from Ghent University. I don't know if I spelled that right. She studied civil engineering at Ghent University, and after the studies, she started working as a PhD researcher in the Department of Structural Engineering and Building Materials of the Faculty of Engineering and Architecture at Ghent University. And she's focusing on structural glass in elevated temperatures and fire, so I think it fits to what we've seen before. And her presentation is about numerical heat transfer model for predicting temperature gradients and fracture in glass planes. So please, Evelien.
Thank you. So good morning, everyone. Thank you for the introduction. So my name is Evelien Symoens, almost right. And today I will present to you one of the things I have been working on in my PhD project. But before we start, I will show you one picture. The people that were here in the previous presentation will know this one, so it's not a surprise anymore. But I wanted to open with this picture because this is a picture of the fire at the Grenfell Tower in London in 2017. And because of this unfortunate fire accident, assessing the fire performance of building materials really became a hot topic. And it's not only this example, there are also other ones, but this is a very well-known one. And they all really emphasize the need for safe building materials. So that is the main motivation behind the PhD project that I'm doing. And that's also one of the things that I will be discussing today. So at Ghent University, we have been working on a numerical heat transfer model that is able to predict temperature gradients if we expose the glass to fire. And then when you have your temperature gradients, you can also predict the fracture. So when we talk about modeling structural elements in fire, you have a general framework that always comes in play. So you have a combination of 3 different models. You have a fire model, a thermal model, and a structural model. So you start with a fire model. From the fire model, you get the heat fluxes from the fire, and you get the temperatures of the fire. Then when you go to the thermal model, you can actually input the heat fluxes, and you will get the temperature fields in your element, so in time and in space. And then you can input the temperature fields in a structural model, and the structural model will really quantify the overall behavior of your element when it's exposed to the combination of thermal loads and mechanical loads. That's basically how it works in general. So the fire model is purely fire dynamics, so it depends on room geometry, it depends on the fuel availability. It doesn't depend on the material that you're using, so today I will not focus on that. But the next step, the thermal model, that's what I'm going to focus on today, because the thermal model, there you really have a distinction between the materials that you're using. And I can show that with this slide, very simplistic. For example, if we talk about concrete, it's an opaque material. If you have a fire, you have your incident heat flux. And all the energy of your incident heat flux will be partly reflected and it will be partly absorbed. But if we talk about glass, you have a transparent material. So with the same incident radiation, you will also have a part that is transmitted through the surface and also transmitted through the whole element. So it's an additional mechanism over there when you compare it to opaque materials. And next to that, that transmission is also very dependent on wavelengths, which makes the whole problem also very dependent for different wavelengths. So as you can see, the problem for transparent materials is different than for opaque materials. So there's definitely a need for a different thermal model if we are modeling with glass. Now, there are different ways to approach this complex thermal model. One of them is doing experimental testing, like Maximilian is doing. As he said, it's quite expensive, so that's like a disadvantage that comes with it. And apart from that, you also have to do multiple experiments if you want to do different configurations. So that's one way to deal with it. Another way is working with numerical models that are already available. But still, if you work with those, it comes with some limitations. So sometimes you have limited boundary conditions that you can apply. Sometimes you are limited in the fact that you cannot implement the wavelengths. So there are always some things that you cannot really implement over there. So that's why we chose to make a model ourselves, that we have full control over the whole calculation, and that we can really play with the model for in the future. So to start with this model, we started in one dimension, so the one-dimensional heat transfer model. And this is purely based on finite difference methods. So I guess some people here in the audience know how this works. So first, when you have your element in the thickness, you discretize the geometry. And then for your internal slices, you have some kind of an energy conservation equation. And it's a differential equation, but because you discretize the geometry, you can approximate it with finite differences, and you can come up with a formula at the bottom, which really gives you actually the temperature evolution in time, in space, for the internal slices. Of course, there are also boundary conditions. Boundary conditions always depend on the situation that you're in. But in a 1D heat transfer model, where you want to model a fire, it's just simplistic that you have on the left-hand side a fire, and on the other hand side, you have an exposed surface. So the boundary conditions for that particular situation look a bit like that. So on the left-hand side, where you have the fire, you have an incident radiation coming in. A part is reflected, a part is absorbed, a part is transmitted, as you can see from the green arrows. And then apart from that, you also have an air layer at that surface. So the air will give you some kind of a convective heat transfer. And then also the temperature of the surface will heat up, so it will also give surface radiation. So that's the boundary conditions for the left-hand side. And if you go to the right-hand side, you have the unexposed surface. So there you don't have an incident heat flux, but you will have still convection because of the air layer at that surface, and also surface radiation because of the surface heating up. So with this figure, you can actually see that you have three different kinds of elements in your thickness. The first one is the one at the exposed side. So what we basically will do in this method, we will check the heat fluxes that come from the left, and we will check the heat fluxes that come from the right, and we balance everything out. So the first element at the exposed side, it has from the left the influence of the absorbed incident radiation. You have the convection, also the surface radiation. And from the right-hand side, you have the conduction of your neighboring slice on the right side. Then all the elements from there onwards, except for the very last one, they all look the same. So I call it element 2. So for them, it's all about conduction from the left side and conduction from the right side, both from the neighboring slices. And then you have the third element, so at the unexposed side, and also there, from the left-hand side, you have conduction, and from the right side, you have the convection and the surface radiation. So if you have all this information, you put in the equations that we typically use for all these heat fluxes, and then you can come up with the formula at the bottom that really gives you the temperature evolution in your element in space and in time. So that's basically how the whole calculation works. As you can see, there are a lot of input parameters, so we have to check them too. So some of them are temperature dependent, as you can see over here. So a lot of them are well known. So you have the density, the thermal conductivity, specific heat in a function of the temperature. And then the fourth one is a special one. It's a convective heat transfer coefficient. It's a very tricky one if we want to do thermal calculations, because it's a bit tricky to have a good guess of this value. So as a first step, what we actually did is we assumed the air to be a laminar flow. So when we assumed that, we could actually make a calculation to have a heat transfer coefficient in function of the temperature. Apart from that, we also have the wavelength-dependent properties. As I said in the beginning, it's an extra complexity that comes in play when we talk about glass. And what I specifically mean is when we have a fire, you have a range of wavelengths that come in play. So the range goes from 0.1 micrometer until 100 micrometers. And it's actually the orange zone that you can see on the right. And we can actually divide this orange zone in 4 different categories. And these categories are chosen in terms of the transmission spectrum of the glass. As you can see on the spectrum, there's like a green region where the transmission is really, really high. So if you then have your balance of your reflection, transmission, and absorption, the reflection and the absorption will be quite low to equal everything out to 100%. So that's the green region. If you look left from the green region, you see that the transmission is 0. So when the transmission is 0, you only have reflection and absorption that's left. And it's the same as an opaque material. So in that wavelength region, we can simplify the model as an opaque material, actually. And the same thing counts for the region behind the purple line over there. Also there, the transmission is 0, so we can really say that the material is behaving opaque over there. And then we come to region 3, the most complicated one when we want to model glass in fire. It's a region where you see that the transmission is decreasing, but not totally. And it's also depending on what wavelength you're looking at. So that's a first complex thing. And as you can see over here in the transmission spectrum, the graphs also depend on the thickness of your glass. So this decrease of the transmission is also depending on the thickness of your glass. So you have 2 influences over there. And as we know, we have our glass surface, so we have the reflection at the surface and then transmission and absorption. So the refraction basically stays the same. So the change in transmission will give a change in the absorption. So that's the relation that we will basically see in this purple region. Now, it's a bit complex. So as a first step, we made use of spectrum averaged values. So these are values that were analyzed by a student at Ghent University in 2017. He did radiant panel tests and actually measured the different values for the transmittance, the absorptance, and the reflectance. And if you put that data in a graph, you can actually see the trend that I was talking about in the previous slide. Because what can you see from the yellow curve, that's the reflection, it stays more or less the same. But as you can see from the absorptance, the blue curve, it increases with thickness. And on the other hand, the transmission, the transmittance, decreases with the thickness. So you can really see the trend that those 2 are connected. So what we did for our numerical model is we made an approximation on this data. So we kept the reflection constant at 15%. Then we made use of a new term. We call it in-thickness absorption. It's something very difficult to measure, so we just made a first approximation over there. We just assumed if we have 1% of absorption for every millimeter that you're crossing. So that was a first guess. And if we implement that in-thickness absorption in a linear expression for the reflection, I mean the absorption and the transmission, you can get an approximation that you can see with the dashed lines, and it fits quite nicely on the experimental data from 2017. So these expressions are also used in the numerical model. So now we have our formulas, we have our inputs, so we can actually start modeling. We also need, of course, some data to validate the model. For that, we will actually do an experimental campaign at Ghent University in the summer. Everything is ready for that. But for now, we did it with some literature that was available. So what I used to validate this model is some data that I got from a paper that you can see over here. They did a radiant panel test on a particular glass, and they monitored the temperature evolution of the exposed surface in red and the temperature evolution of the unexposed surface in blue. So when we compared the experimental data with the numerical data, we saw that it fitted quite nicely. At the left side, you can see all the temperature evolutions of the different slices in the discretized geometry. It's a lot of information on one slide, so actually the one next to that is more clear. There you only have the graph of the exposed element and the unexposed element, and as you can see, the data fits quite well on the experimental data from literature. Of course, because we are modeling numerically, we can also then make a graph of the in-thickness evolution of the temperatures. That's something that we cannot really observe in experimental testing, so that's also an advantage that we can get from this numerical model. Now, because the model is validated, it works well, we took the opportunity to do a sensitivity analysis. And the sensitivity analysis was not only to know what is the influence really of all the input parameters, but we also wanted to assess the importance of the scatter that we have on some input parameters in the literature. So it's basically a combined sensitivity analysis of different aspects. And we came up with some, actually 4 levels of importance. And as you can see, the input factors on the top are the most important to assess properly, to have a good and accurate result in relation with experimental data, and then the level actually decreases a little bit when you go down. So as you can see, the most important factors to assess properly, to have a good numerical assessment on your experimental data, are the incident heat flux, the convection coefficients, and the reflectance. So we know if we will do experiments that these factors will be very, very important to do an extra effort to get them as accurate as possible. And you can say the same of the other input values, but the importance decreases when you go down. So then I started working on the 3-dimensional heat transfer model. I want to say over here, it's still a work in progress, so the figures are not final yet. It still needs validation, some fine-tuning at the edges. It's not ready yet, but I just wanted to show this to show you why we do all this effort to make this model ourselves, because it really gives us a lot of freedom on modeling different configurations. So what you can see over here, this is the same situation as what we modeled in the 1D heat transfer model, with the only difference I want to note over here, the thickness is over the x direction, but the axis is a bit enlarged. So just to make sure that you can see the different colors in the thickness, so it's normally way, way smaller, that you don't think the glass is really thick. But then you can really see how the heat is propagating in our glass. And the main reason why we do this is, now you have heat coming from one surface, but when we talk about structural glass, it's also something that Maximilian also showed. When you have a beam, for example, you have heat coming from 3 sides. And a lot of thermal models don't give you the freedom to model these boundary conditions all in detail. And if we have a 3-dimensional model that we control totally by ourselves, we can implement this on the 3-dimensional model. So that's the aim of this 3-dimensional model that we are working on now. And we will also validate this with the experiments that we will do in the summer. But still, this is not final, so the figures are not yet validated. Just keep that in mind. OK, so that brings me to my last slide with the conclusions. So today, I actually showed you that there's a need for a detailed thermal model when we model glass in fire. So we did a first approach with a 1-dimensional heat transfer model where we used the finite difference method, but we put some extra attention over there on the spectrum averaged values to implement the wavelength dependency when we talk about fire. And also we did a first attempt on the in-thickness absorption. From that heat transfer model, we then validated it with experiments, and we saw that it worked quite well and actually duplicated the reality. Then we did a sensitivity analysis on this model where we could see what the most important parameters are to assess properly if we want to model the reality as much as possible. So here you can see again the 4 different levels. And then in the end, the 3-dimensional heat transfer model still under construction, but we are getting there, and we will validate it with future experiments that we will do at Ghent University. So that brings me now to the final slide of this presentation. I'd like to thank you for your attention. Hope you learned something from this. If there are any questions, please ask. I'm here the whole conference. You can always approach me. And yeah, thank you.